Hello everybody.
Hello.
Hello. Good evening from there, in the south of France, where I'm spending my holiday today with my Minilac, FX electric, self-launching. And it's my honor and pleasure to report on the development project for a hybrid electric propulsion system. It is entitled Erop for electric and rotary engine hybrid plane. This project was initiated by Stefan Sänger from Atlantic. He's the head of Atlantic. And further development partners are Klein and Erop, Z Design, and critics to look up, who is also giving a presentation this day, I think. And my task in this project is the development of the drive battery. I'm from the University of Cooperative Education in Mosbach, and I'm the head of the Department of Mechatronics and Electromobility. I was also involved in the projects of Binder EW29D Electro and Schleicher ASG 32 Electro, which is also in Sweden, I think, now. I have already given this Erop presentation at Erop in April this year and at the Battery Experts Forum in Frankfurt in July. The development goal of the Erop project is to achieve the maximum performance of a hybrid electric drive with the current state of technology. It's obvious that we need the outstanding aerodynamic efficiency of a glider as a development and test platform. We use two different energy sources, battery pack and optional electric generator driven by a rotary engine as a range extender. Further advantage of the glider is a lightweight construction, and to optimize the workload for the pilot, a simple monolever control of the drivetrain will be used in the cockpit. Here you will see the main components of the system. In the nose, could you see the mouse?
Yes. Yes.
Okay. In the nose, the electric motor with the foldable propeller is from Z Design, and the wings, will be the new developed battery. This is the old one of Antares. In the primary engine compartment, you can see here, the power electronics and the rotary piston engine with the generator and fuel tank. Aerodynamically integrated into the surface of the fuselage contour are the newly developed heat exchangers for the combustion engine and power electronics. There is no additional drag. And the most efficient cooling due to the turbulent flow at this point. So, to overcome a known disadvantage of electric propulsion, which is the comparatively low energy density of approximately 260 watt-hours per kilogram compared to 10 kilowatt-hours per kilogram for petrol, it is necessary to use the unsurpassed aerodynamic efficiency of gliders. The Antares E1 has optimal characteristic as a test bed and development platform. We have excellent quality as a glider. We have a high fuselage and high landing gear, enabling a large diameter propeller with 1.2 meters at the nose. We have a spacious engine compartment providing room for the rotary engine and fuel tanks, approximately 35 liters. And the existing battery compartment in the wings can be used for the new battery. The internal fuselage structure is very suitable to adaptation of the front propeller drive. The calculated performance of this glider or plane is maximum blade ratio of 44. We subtracted 2 points for the propeller, which had been measured by Ackerflieg. We have a maximum takeoff weight of 660 kilogram, water ballast capacity of 210 to 350 liter, and expected battery capacity of 17.4 kilowatt hours. The maximum range in powered flight would be 2,500 kilometers and an endurance of 14 hours. The specification of my new battery is given by the former one, is voltage one, and for the motor and the power electronics is 216 volts to 288 volts, weight approximately 77 kilograms, maximum length due to the compartment in the wing is 2,700 millimeters. Maximum current is 130 amps peak. Power is 36 kilowatt peak, and continuous power required is 15 kilowatt continuous. Energy, as you see, as much as possible. And the energy as a high performance and safety. We choose, I will argument later on, we choose 18650 cells, and we choose a configuration 27 cells in serial and 22 cells in parallel. This means that we have in both wings 1584 cells. The reason why we choose the 18650 cells are summarized here. There are a lot of cells available on the market. Here you see also the cylindrical cells of Saft, which has been used in the past, or actually in the Antares. And you see also other cylindrical cells. 18650 cells will be used by Tesla, or 21700 will be used by Tesla, by Tesla, and we have prismatic cells which will be used by automotive, for example BMW or Audi, and VW uses these pouch cells. But we decided to use 18650 cells. The main reason was safety, because every cell has an integrated fuse, which is Erop, as you know. I will show later on the function of this SID. Each single cell has a small amount of energy within a metal housing, approximately 10 watt-hours per cell. And you have redundancy because you use a lot of cells in parallel, in our case 22. And so if one cell fails, it's not really a problem. It's a problem, but not existential. Further on, the availability, you have many different manufacturers and providers for this cell type. It's a high volume product in millions numbers, and normally it's low cost due to competition and high production quantities. But actually, due to the need for the automotive industry, the prices increased and availability reduced. Further on, you have a wide selection spectrum for optimization, concerning chemistry, energy density, and power density. Further on, you have a high reproducibility due to high production numbers. The form factor, the small cells, 18 millimeters in diameter and 65 millimeters in length, is an advantage because they can be easily adapted to complex shape of fuselage or wing. And further on, the dimensions are standardized. This guarantees interchangeability. But there are also disadvantages because you have a lot of cells, more than 1500, and they must be connected electrically and fixed mechanically within the housing, in the fuselage or in the wing. So I have told about the safety aspects, and this shows one of the main safety aspects of 18650 cells. The integrated current interrupting device, SID called, you can see here the cross-section of an 18650 cell with the cell inside the coil, and on the top there is the positive terminal. You see the positive terminal, then you have a burst disc, insulating ring, and the current collector disc. And burst disc and current collector disc are connected via a point here, you see here. And in case of there's something wrong, overheating or charging short, mechanical abuse or something else, this leads to a potential increase and a chemical reaction of components within the cell, producing gases and a lot of energy. This increasing pressure inside the cell. This is called a thermal runaway. The increasing pressure will finally open the burst disc at the positive terminal. Further on, the cell will be vented to avoid uncontrolled explosion. And the electric connection between positive terminal and current collector disc will be disconnected. In case of parallel connected cells, which is in our case we have 22 cells in parallel. In case of parallel connections, the cell will also disconnect from all other cells, ensuring further operability of the battery package. And because of the comparable low energy content in an 18650 cell, approximately 10 watt hours, as said before, a chain reaction of thermal runaway to other cells surrounding could be avoided. But this has to be demonstrated for certification process in a battery pack. I will show this later. Are you still by me? Is it working?
Yes, excellent.
Okay, thanks. This, as shown before, a lot of different cells of 18650 format are available. The task is now to identify the most suited cell for the desired application. Based on the requirement, you can use the data sheets for pre-selection of cells. But you have to evaluate the cell real performance under conditions which represent the mission profile. This shows the estimated mission profile for our project. We have takeoff 1 minute at 35 kilowatt. Then we have a Klein phase 5 minutes at 30 kilowatts, and then we have a travel flight at 10 kilowatt. This means you see here the cell voltage and cell current, and here the power in kilowatt for the whole battery. This is for a single cell. So we have currents of 7, 6, and 2 amps, depending on the flight phase. But the whole process, whole cycle, one cycle, charging, discharging, is also charging. And we charge in this test cycle with 2 amps. In practice, it would be much lower. Or also the travel flight would be much lower. We need only 7 kilowatt for travel flight with the Antares, but we made a compromise to reduce the cycle time. So in this case, we have a cycle time of 4 hours. This will be measured automatic or computer controlled. And in the next phase, you see a slide, you see a complete profile, including the charging part. This test profile is a compromise, one important selection criteria is the temperature increase of the cell during operation. And this diagram shows the temperature increase of different pre-selected cells. For some cycles of the mission profile, the different temperature behavior is a result of different internal resistance. Higher internal resistance causes more energy loss, and higher temperature during operation, and finally less usable energy for the propulsion itself. And further on, this shows the equipment in our battery lab for lifetime and performance evaluation of different pre-selected cells. You see the cells within the holder here, for example, and the others are here, and covered with fiber to avoid heat exchange in this case, because we use no cooling in the wing or in the plane or the battery pack, and so the battery has to fulfill the requirements without cooling. That's our goal. So you see the results. This diagram shows the lifetime evaluation of 8 different 18650 cells and one 21700 cell. We choose only one 21700 cells, to compare. But on the point of energy density, it makes no sense. It has nearly the same energy density, but the disadvantage you see is a short lifetime. What we see here is on the y-axis the energy, discharge energy in watt hours. And on the x-axis you see the cycle number. 1000, 2000, 3000, 4000, and so on. And you see there is quite a lot of differences between different cells. First, the initial energy are different, the primary energy is different, and the decrease of energy according to the number of cycles are also quite different. The lifetime of a cell is the number of cycles until the usable energy has decreased to 80% of the initial value. And the diagram shows impressive differences in initial usable energy and also impressive differences in lifetime. We decided to use cell number 1, which is the light blue one, you can see here, has a quite high energy and a quite high lifetime. And the parameters for the cycles are shown here on the top, At this stage, we didn't decide if we use 24 in parallel or 22 in parallel. Later on, we decided to use 22 in parallel, so the parameters different. But nevertheless, we choose this cell number 1, like you, and use this for further evaluation. And this diagram shows the lifetime evaluation of 7 cells of the same type to evaluate lifetime and reproducibility. In this case, we do not charge to 4.2 volts as before, but we reduce the voltage. It's acceptable concerning the energy content, but it increases the lifetime, as you can see here, comparable to the former diagram. And you can see the cells are quite reproducible until 2,500 cycles, and then there occur difference between some cells. But it doesn't matter, because we have in every package, we have 22 cells in parallel. So if one cell in each package is a little bit lower in performance, it doesn't matter, it will be compensated by the other cells. But 2,500 cycles is a lot. I will show you later on. So are you still by me?
Yes.
Okay. So further on, we have to demonstrate further performance tests. First is the discharging at high currents, and second is the some runaway tests, which are required for certification. And so we prepared some blocks of cells. You can see here 3 blocks, each of 22 cells in parallel, and in each package we prepared 2 cells. They were stripped with the plastic outside. They're stripped and we put a heating coil around. The heating coil is necessary to drive this cell in a thermal runaway and to check what happened if you drive one cell in a thermal runaway. The first test was high current. You can see here, I tried, the video is working. This is bonding, contacting each cell in the base plate of each package. It will be done by bonding. This is small thin aluminum wire. It's also a fuse base on this third package. And we mounted 3 cells in serial and 22 in parallel. These are the connections for the heating wire to drive this corresponding cell into thermal runaway and to look what happened. And then we have different temperature sensors in the package to check what happened. And the first test was looking the temperature development of this package during high current of 130 amps. We have measurement equipment. We have a data logger for bell voltages and temperature. We have an infrared camera to see the temperature distribution at the surface of the cell and to see if there's any hotspot on the connections between the cells. And we have the high power current cables here for the 130 amps. And the result is shown here. We have the current. The red curve is 130 amps. The temperature increased during the operation and the cell voltage decreasing with the state of charge. And you see, we can approximately 25 hours of full power. If you compare to a combustion engine or Rotax, you can use only 5 minutes of full power, according to the manual, for example. So we are nearly able to discharge, not complete, but nearly complete, with full power with 130 amps. That was the goal without cooling. We are still in the range of the allowed parameters of the battery cell. You see only a homogeneous temperature distribution on the battery surface. This was a test at high power. Then we make thermal runaway tests. You can see here the experimental setup for thermal runaway test for the certification process. We have to demonstrate that a thermal runaway of a single cell would not lead to a thermal runaway of other neighboring cells. There should be no chain reaction. So we do that by a single cell being driven into thermal runaway by heating cells on different positions in a 22 parallel package. We have these different cells prepared with a heating coil. You can see here this prepared cell. And the setup is an open tube surrounded with 10 millimeter polycarbonate glass plates, which are very resistant. And we measure, during the process, we measure the cell voltage temperatures at different positions in the battery pack. We have an infrared camera and a visible video camera with high speed camera to see what happened. And this have been used for documentation. Here, this is a video, I hope it works. It shows on the left side, it shows the action of the SIT, the overpressure fuse quasi. You see that? And then we have to, according to the certification process, normally the current would stop at this moment. But the EASA and LDA wants that we heat further on until a thermal runaway occurs. And this will on the left side. First we start on the left side, sorry. Hope it works. You heard sound, smoke, and that was it. SIT opens, disconnect the battery, this could be seen later on, and everything is okay. But the certification process requires further heating, and 3 minutes later, this happens. I hope the video is working.
Yeah, we could get the idea. It was not running at a very high frame rate, but
it's also always in slow motion.
But we could get the idea.
I can summarize the results.
Yeah.
First, the fire is self-distinguishing. You will see, and there is no further chain reaction. There is no surrounding cell driven into thermal runaway. We continued measurements more than 1 hour after this event, and there was no further effects, no thermal runaway. In detail, you can see the measurements. You see the temperature of different temperature sensors, and the voltage is the green one. The voltage is the voltage of all 22 cells in parallel, but you can only measure one voltage because they're all in parallel connected. But you see two effects here. Here first you see a temperature increase, small. This is when the SIT opens and hot gases come out of the cell. This leads to a temperature increase, and then approximately 3 minutes later the thermal runaway will be triggered approximately at 125 degrees. Then the temperature increases very rapidly up to 1250 degrees. The voltage drops down a little bit, but then increases again. You see it in detail. Now it's enlarged, the point of thermal runaway. You see here the voltage of the cell package with a decrease of a few hundred millivolts, 222 millivolts. Then you can calculate according the internal resistance that there is a current of 125 amps, a shortcut via the cell in thermal runaway. All other cells in parallel will be shortcutted via the cell under the test here. The maximum temperature approximately 1250 degrees. You see, and the voltage comes back to more than 4.1 volts. This means the battery is still operating. You can fly further on. It's not a nice impression, but it works. So, you see in detail, in detail here, we use a fiber reinforced plate to protect the next battery, but this failed because the kinetic energy of the cell insert, which we've blown out, penetrates this block. In the actual state, we use small 0.5 millimeter thick titanium sheets which withstand this effect. And you see also the additional fuse. These are the bonding wires. We use 2 for each cell, and each bonding wire is an additional thermal fuse. And you see here, this was a cell which was driven in thermal runaway. Then there was a current of approximately 121 amps, and the aluminum wire melted and protects all the other cells here surrounding. They are still on a voltage more than 4.1 volts. So, summarizing the battery performance, we have a voltage of 216 volts up to 299 volts depending on the level of charge. This means between 3 volt and 4.15 per cell. The weight is a little bit higher, approximately 80 kilogram. Length is also a little bit higher due to the conductors between these there and the signal. The maximum current 130 amps is not a problem, more than 20 minutes. Maximum power, resulting power approximately more than 36 kilowatts. Continuous power, no problem, more than 50 kilowatt. The energy is in this configuration due to higher losses because we use 10 kilowatt instead of 7 kilowatt for travel flight. We have 16.6 kilowatt, but on the real profile, if you use only 7 kilowatt on the travel flight, we have a real capacity of 17.4 kilowatt. This means only electric, we have a range of 350 kilometers or 3 hours, including takeoff, climb to 1200 meters. The battery lifetime is more than 3,000 cycles to 80%. This means more than 1 million kilometers or 9,000 hours of operation. My question is, has one of you more than 9,000 flight hours?
What is the life cycle of a Rotax engine? Is that 1,600 hours, something like that?
2,000 Rotax, maximum 1,000 hours, I think, or 1,200. I don't know exactly.
Oh, yeah, but the battery can take much more than that, I guess.
Yeah. So we have to do additional tests have been made, structural certification of the motor mount in the front, in the nose, and of the motor compartment for the Rotax engine. And this has been made at the DLR in Stuttgart. And the maiden flight was in May this year, was successfully, and actually there are further test flights making by Stefan Sänger. So, I'm already now, I'm still in the Klein, point landing. The contact data of Stefan Sänger, if you're interested in my contact data, and I'm open for questions now. Thank you very much.
Okay. Thank you so much, Rainer. Very interesting presentation about battery technology. I'm sure that this was probably the most detailed presentation anybody in this room had about the delicate world of batteries. So I wonder, in the audience, is there any questions now for Mr. Klein?
Yes, I have one question.
Yeah.
How bad are the gases coming out of the battery?
Yeah, they are toxic and burnable. So you have to avoid that these gases could enter into the cockpit. And this is guaranteed because the wing compartment has no connection to the cockpit. So the wing is also vented on the downside, the venting flap. So if there is an accident and some cells run into thermal runaway producing gases, for example, we tested to show that there is no thermal runaway if you have a single cell in thermal runaway. There is no chain reaction. And a single sail produces approximately 10 liters of gas to get an impression what happens. But you have to avoid, in any cases, and this is also to demonstrated by the certification process, that there are no circumstances could these gases enter into the cockpit.
Rainer, I would like to ask, do you use the same venting technology as the original Lange Antares with the opening under the wing?
Yeah.
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 Yeah. Okay. Okay, any other questions? Then I think we should give a very big hand again to Rainer Klein. Thank you, Rainer, and I hope you will enjoy the rest of your flying holiday in Serre with your mini-lac this.
Yeah, sorry, I've forgotten to switch the light on.
No problem.
I'm sorry about that. I can see the.
Yeah.
Sorry.
Yeah.
Okay, I wish you further a nice conference and hopefully a lot of test flights. I will do the same.
Yeah.
And tomorrow I hope I can fly also.
Okay. Thank you. Okay.
Bye-bye.
Bye-bye.
Bye.